Hello and welcome. Today we are going to discuss about gravitational potentials. Now, gravitational potential is the potential energy per unit mass. So, suppose the potential energy of suppose some change in potential of some mass is Vb minus Va, that is, and this change in potential is equal to change in potential energy Ub minus Ua by the mass of that particle. So if we consider this as V, or if we consider this initial potential as 0, so we'll get V is Ub minus Ua by m. So simply we can see that the gravitational potential is simply the difference of potential energy per unit mass. So now we are going to solve an example. We are going to consider an example, that is the potential due to a point mass. So we consider this the point mass m, and at a distance r we are going to consider the potential at the point P. Okay, and we consider this point as the point A. So from this equation we can write the potential of this point P can be written as UR minus U infinity by m. M is the mass of this particle. Yes, so we can write here that UR minus U infinity minus GMM by R, as we have seen from previous examples that the potential energy is minus GMM by R, and you can easily see that at infinity the potential energy of the mass is 0. So the difference in potential energy is minus GMM by R. So, and the gravitational potential, as you can see, is R minus U infinity by m. So what that gives us is V equal to minus G m by R. So by m, sorry, this mass will be m, and Gm by R. So the gravitational potential due to a point mass m is at a distance r is V equal to minus Gm by R. Now we will consider another example, that is the potential due to a uniform ring at a point on its own axis. So let us consider this is a uniform ring, that is the mass of this whole ring is uniformly distributed over its circumference, and we are going to consider its potential at a point on its own axis. So it's the axis of this ring is this one, and a point, let us consider this point P. Okay, and here we are going to consider the potential. So you can see that we will not consider the whole ring at once. We will consider small mass elements dm, and we will calculate the potential for these mass elements at this point, and then we will integrate over the whole ring. So if the radius of this ring is a, and this is r, the distance at which we are measuring the potential is r, and this makes angle theta, this circumference element with this thing makes angle theta. then and we can easily see this is root r square plus a square. For now we will write this as z. And now we can get the potential due to this small mass dm as dv equal to, we have we have seen just a while ago that the potential is given by minus gm by r. So we can just write g dm by z. Z is this. So z is root r square plus a square, so we can write also g dm by root r square plus a square. Now to integrate, to find the potential due to the whole ring, we will need to integrate for the whole mass. So we'll just do that. V equal to integration dv equal to minus g dm by root r square plus a square. See that this root r square plus a square thing does not vary for the for any dm. If you consider dm here, this distance from this point to this point would just be the same as this root r square plus a square. So the only thing that the integration is over is this dm, and if we integrate this dm over this whole circle, over this whole ring, that gives us m, that is the mass of this ring. So that gives us minus gm by root r square plus a square. And as we have seen, root r square plus a square is z, so we can write this as minus gm by z, where z is the distance between the point P and the length element of this mass element, sorry. So we have found the expression for the potential of potential, the gravitational potential due to this ring, due to this uniform ring. And up next, what we are going to see is the potential due to a solid sphere.